In this mini lecture, I'm going to look at logarithmic functions. So if you think about it, we have two ways of writing the relationship between the numbers 5 and 25. I can say 5 squared is 25, or I can say the square root of 25 equals 5. Now, that's really the same relationship, just expressed two different ways. We could say that this first one is squared form, and the second one is square root form. And if you really think about it, what changes between these two forms is which number you start with and which number you don't know. If I have 5 squared equals what, that's sort of squared form, right? And we can answer that. We could put other numbers instead of 5 in here, right? 7 squared is 49. 10 squared is 100. This other question says, well, what if you start with the result of the squaring? What would you have had to start with to do it the other way? What is the square root of 25? What is the square root of 49? What is the square root of 100? So which number is given and which number is requested, they sort of change between this. We can do something similar with this. I could say 2 to the third equals what? And we know 2 times 2 times 2 is 8. But then I could change that question and say 2 to what power is 8? So I know the result, and I need to know what that missing exponent would be. 2 is my base. What exponent would I have to have? To do that, we invent this thing called a logarithm. And a logarithm is just this idea of having a missing exponent, so that I know what the base is, I know what result I want, I need to know what exponent will get me there. If this was 2 to what power is 16, it would have to be 4. Okay, so we write this, and we read that y equals the log base b of x. And the definition is just, and this is just some technical stuff here, I can only take the log of a positive number, so x has to be greater than 0. Just like with exponential functions, my base has to be greater than 0 and it can't be equal to 1. But if I say y is the log base b of x, that really means y here is my missing exponent. How would I change b into x? So b to what power is x? And this y here, that's my missing exponent. That's what the logarithm is, right? So the log is a missing exponent. Okay, ran out of room there. The log is a missing exponent. So this definition establishes two different ways of writing the same relationship between two numbers, just like I have up here with squared form and square root form. What we have is something we can call exponential form and something we can call logarithmic form. These first few problems we're going to go from left to right. We're going to start in exponential form and then rewrite in logarithmic form. On these last three we're going to go the other way. We're going to go from logarithmic form and write in exponential form. So if I go from left to right, we're switching to logarithmic form. If I go from right to left, we're switching to exponential form. And we should be able to go back and forth either way. Here's the other thing I keep in mind when doing this. Notice, what's b here? Log base b of x means b to a power. B in both of these are what we call the base. So another saying I keep in mind with logarithms, when you switch from one form to another, the base stays the same. The base stays the same. So when I look at this first one, exponential form, 2 to the 3 equals 8, what's my base? My base is 2. So the base stays the same. So I have log, and then I need a base. It's going to be base 2. And it's got to be log base 2 of something equals something. What is the log? The log is a missing exponent. So what is my exponent here? It's 3. So the log has to be equal to 3. And so 8 only has one place to go. I also sort of think of this sort of physically. When I see a log like this, it's always the base to the power, and to get the power you have to go across the equal sign. 2 to the third power equals 8. These two statements say the same thing. It's just what's given and what's requested changes. Here I know the 3 and I'm looking for 8. Here I know the 8 and I'm looking for 3. Okay, and the second one then, 1/25 equals 5 to the negative 2. What's my base? Yeah, the base is 5. So the base stays the same. So log base 5 of something equals something. The log is a missing exponent. What's the exponent here on the left-hand side? 5 to what power? Yep, -2. And then the 125th, well, there's really nowhere for it to go except here. So the log base 5 of 125th is equal to -2. If I wanted, I could put the 125th in parentheses. Remember, this is true. Remember, negative exponents mean take the reciprocal. So that would be 1 over 5 squared, which is 1 over 25. And then here, I don't have a specific thing I can check. I could figure out what y has to be. I guess it would have to be 2, right? 4 squared would be 16. But how do I just rewrite this? What's the base? What's the base over here on the left? Yeah, what's the base? 4. The base stays the same. So log base 4 of something equals something. What is the log? It's equal to the missing exponent. What's the exponent here? Y. And the 16 then would have to go here. So we'd have log base 4 of 16 equals y. Okay, let's go through these others a little more quickly. Hopefully you're getting the hang of this. Now I'm going to go the other way, but it doesn't matter which way we're going. The base stays the same. What's the base here? Log base 3. So I get 3 to some power equals something else. The log is equal to the exponent, so the 4 is my exponent. 3 to the 4th equals 81, and of course that's true. 3 times 3 times 3 times 3 is 81. Okay, this next to the last one. 3 equals log base b of 64. What's the base? The base is b. So I'm going to have b to some power equals something. My power is what the log is equal to, so it's going to be b to the 3rd equals 64. And finally, on this last one, log base 3 of a equals x plus y. What's my base? 3. What's the exponent? What the log is equal to is the exponent. So 3 to the x plus y equals a. All right, so we're going to do a couple more problems just practicing going back and forth from exponential form to logarithmic form. So write in logarithmic form. Remember, the base stays the same. So what's the base here in part A? It's 3 to the 4th power, so the base is 3. So I'm going to have base 3. The log is equal to the exponent, or you can say 3 to what power? We have to go across the equal sign. So log base 3 of 81 equals 4. I think we had that on the other side, didn't we? I should have made up a new example. Well, anyway, so here in part B, what's the base? What's being raised to the power? The a. So I'm going to have log base a of something equals something. The log has to be equal to the exponent. The exponent in this problem is 2. And then this would have to be where my 3x would go. So that I've got a to the 2nd power is 3x. 3 to the 4th equals 81. We always go across in that way. That, I think, actually makes it easier than to do these. Writing in exponential form, I just start with the base, 10. 10 to what power is 1,000? 10 to the 3rd is 1,000. We go across like that. And then in part B here, what's my base? Log base x plus y is my base. X plus y to what power? The power is 3q. Oops, no, that's not what I want. Yeah. The power is 3q, and that's going to be equal to 2. Okay. So that's just practicing going back and forth, sort of between these forms. Often what we have is we're just asked to evaluate some logarithms. It's helpful to think of the logarithm in this case as the missing exponent, like I've said. And what I can sort of do here is log base 10 of 100 equals what is what we're sort of saying. Well, I can rewrite that then in exponential form. That would say 10 to what power equals 100. and so I see that that logarithm would have to be 2. Right? 10 to the second power is 100. So over here, again, this is really saying then 5 to what power equals 125. Well, I know 5 times 5 times 5 is 125. So that's 5 to the third power equals 125. So the log base 5 of 125 is equal to 3. In this one, then we'd have 3 to what power equals 1/9. Well, I know 3 to the second power is equal to 9, but that's not exactly what I have here. I need the reciprocal. Remember, for a reciprocal, I need a negative exponent. So 3 to the negative 2 would be 1/9. And so this logarithm is equal to negative 2. These next two are a little bit more complicated. We've got here 36 to what power equals 6. Well, how do I make a number smaller? This isn't a reciprocal, right? Negative 1 would be 1 over 36, right? If I had 36 to the negative 1 or 36 to the negative 2. What's important here is to realize that going from 36 to 6, what that really is a square root. So how do I take a square root by using an exponent? We have to go way back to a couple chapters ago when we did radicals. To get a square root, that's the same thing as a fractional exponent. Remember, 36 to the 1/2 power, this 1 would be the power that I'm taking, and this 2 would be the root. So if I have 36 to the 1/2, that's equal to 6. Because 36 to the 1/2 is equal to the square root of 36, which is equal to 6. So the answer to this problem, the log base 36 of 6, is 1/2. If this had said log base 36 of 5, I'd be out of luck. I wouldn't be able to do this. You can do it on a calculator maybe with some other stuff, and if you knew how to do that, we have something called the change of base formula and all of that. But I'd be out of luck. I could do log base 49 of 7, because the square root of 49. It could be a cube root, right? If I had log base 8 of 2, that would say 8 to what power is 2, and that would have to be a cube root. So log base 8 of 2 would be 1/3, just as another example there. So that would be a separate example, perhaps. This very last one down here, again, this says then 1/12 to what power is 12. And if I write it like that, then I see what I need to do is take just the reciprocal, and to take the reciprocal then, that's the negative first power, right? So this answer would just be -1. So work on those a little. You'll want to practice that. They're really not that bad if you think again of this logarithm just being a missing exponent. Just a couple things here. There's some basic properties we have. These are pretty easy logarithms. We do them the same way. We just say 7 to what power is 1. Well, to take a power and get 1, that has to be 0. But then that works for any base. 12 to what power is 1? Well, that has to be 0. And so what that really shows down here in number 1 here, the log base b of 1 is always 0. Whatever base, it doesn't matter what base b is. If you're taking the log of 1, you always get 0. Here, this says 7 to what power is 7? Well, that would just have to be 1. And this says then 12 to what power is 12? That would just have to be 1. And what we see here is that the base and what I'm taking the log of match up. And if that happens, we're always saying then 7 to what power is 7, 12 to what power is 12. Here, b to what power is b? Well, to take b to b with a power, you have to take the first power. So these are two of the most basic properties of logarithms that we have. If we take the log of 1, we always get 0. And if we take the log of the base, we always get 1.